All right. Well, welcome to Lab 1, everybody. I have, if anybody wants to take notes on hard copy papers, I have them up here. I have the digital one on Moodle as well. Does anybody have questions from the Lab 0 stuff about lab reports in general, uncertainty, any of that? Okay, cool. So this lab demo is very likely not going to take the whole time like last time, so I'm just warning you guys ahead of time. But we're already into lab number 1, so hopefully what we talked about in lab 0 will set you up for a good foundation for having a successful first lab report. So let's just dive into it now. And I will note, I have, I'll post my annotated notes here onto Moodle. There's also a lab handout that covers essentially all the same stuff, but with more words. It says the same things. So, okay. So in this lab, we are going to be using different flow measurement methods to practice finding experimental uncertainties. For 2 types of flow measurement instruments. And then we're also going to practice calibration of scientific equipment. All right. The equipment that we're going to use in this lab is made by Armfield. It's a flow meter demonstration unit. There's a schematic right here on the board. And then we're also going to be using a hydraulic bench. So that's what's sitting right over there in front of the sink. So the orange and white thing, that's our hydraulic bench. So that's going to basically provide water flow and then a place for the water to go after it goes through the demonstration unit and then it circulates in there. And then this schematic is the sort of the rig that's sitting right on top of that. So a few things that I want to make note of on here that we're going to refer to a lot when we talk about operating that thing is there is a flow control valve, which is red. So I'll make it in red here. So this is our flow control valve. It's on the upper left of that system over there. We also have an air bleed screw, which is a little screw right here. And then we also have, not pictured on here. So on the hydraulic bench, is a flow, not the flow control valve, the bench valve. So that's not pictured on this schematic, but I will point it out on the equipment over there in just a second. And then, so the goal of this experiment is to look at different types of methods for measuring flow rate. 2 of the key ones that we are going to be looking at in particular are an orifice plate meter. So this is a zoomed in version of it, but it is right here. So it's at the very top of the equipment. And again, I'll point all of this stuff out once I move over there to show you how it works. And then we also have the Venturi meter. So this is down at the bottom, and then the zoomed in view of it is right here. And then we also have a variable area flow meter right here. And that's to the right-hand side of the apparatus. This picture right here, just for reference, this is a side, like a profile view. Okay. Okay, so the orifice plate meter and then the Venturi meter are types of flow meters that make use of the idea that if you have an incompressible fluid, which we're going to be using water, that's an incompressible fluid. When the velocity increases, pressure decreases. All right. This idea of pressure decreasing when velocity increases is explored in a lot more detail in ME 3500, which is fluid mechanics, if you are a mechanical engineering student. And kind of the end result of this discussion is in the lab handout, but I don't love the idea of just using equations blindly. So I'm going to show you where it comes from and we'll walk through it. But just keep in mind that sort of this derivation isn't really the topic of this class or this lab. I just want you to know where it comes from. Okay. All right, so essentially, these flow meters make use of two big equations. One is conservation of mass, and then the other one is the Bernoulli equation. Conservation of mass is pretty simple. It's kind of like our conservation of energy, which we've been talking about in class, where what comes in must go out. All right, this is just another way of saying matter cannot be created nor destroyed, right? So if you have an open system where mass can flow in and out, so this is our open system. If we have mass in, that has to be equal to the mass going out. Make sense? Otherwise, that would mean if they were not balanced, then that would mean we're creating or destroying mass inside of our little open system, which we cannot do. Okay. So essentially, what this means is that the sum of m dot in is equal to the sum of m dot out. So this is our mass flow rate. And we can rewrite this in another way as density times the velocity going in times the cross-sectional area going in is equal to the sum of the density of the velocity going out times the cross-sectional area going out. All right. Something to note here is that this term, V times A, is our volume flow rate. And it is given the symbol V dot. And it has units of length cubed per time. All right, so hence volume flow rate, volume per time. Does that make sense? Okay, cool. All right, so this is our conservation of mass equation. And then our Bernoulli equation is essentially an energy equation. And it looks like this. So we have, if we have pressure in one location plus 1/2 the density times the velocity at a location, at our first location, plus rho GH at our first location, this is going to equal to the pressure at some second location plus 1/2 rho velocity at the second location squared plus rho GH at the second location. All right, and so the reason that this is an energy equation is we have, hopefully the familiar kinetic energy. And this is kinetic energy per volume. And that shows up on both sides. And then we also have what looks like potential energy. Again, per volume. And then this pressure term that shows up is pressure energy. Okay, so this is basically the same thing as when we talked about conservation of energy. All the energy has to be accounted for between points 1 and 2, but it can change its form, right? So we can shift from kinetic energy to potential energy or potential energy to pressure energy, the same as how you're used to thinking about energy. Okay. It's very important to know, and I harp on this in 3500. So if I see you in 3500, you'll hear it many, many more times. But this equation is a very highly idealized conservation of energy equation. All right. So it makes several very key assumptions that if these are not true, this equation is not going to do a great job. Okay. The first one is that we are assuming with this equation that there is no friction in the system. It's a pretty big assumption, right? We're also assuming that the flow is steady, meaning that it doesn't change with time. I already said this before, but we're also assuming incompressible fluid. No heat transfer. And we're assuming a laminar flow, meaning no turbulence or chaos in the flow. And this last one essentially means that if we have our fluid flow, we need to be able to say that I can draw an organized straight line from point 1 to point 2. All right, so this is what laminar would look like. If you were to trace the path of a little fluid particle moving through this flow, that's what a laminar flow would look like. Whereas a turbulent flow would probably do something like this. Okay, so we generally know when flow is turbulent, it's pretty chaotic. And when you see it, you know it. Okay. Any questions so far? All right, cool. So these are our two equations. The second one requires a lot of work for the assumptions, but we can put them together to come up with a prediction for the volume flow rate if we know the density of the fluid and the pressure drop between 2 points, and then the difference in area. So if we go back and look at our flow meter devices, we have, if you'll notice, both of them have different variations on flow basically passing through a constriction. One of them is a sudden constriction and one of them kind of tapers down nicely, but we know we have an inlet diameter D1 and then a tapered diameter D, this should be a 2. All right, so we have 2 diameters there. The inlet and the outlet, so we're going in this direction. Okay, and so what we're gonna do is we're gonna put our conservation of mass and our Bernoulli equation together. So let's start with conservation of mass. So if I just draw the apparatus, we essentially have this. So we have a big inlet diameter, and then I'm gonna call this lowercase d as our smaller outlet diameter. And I'm gonna draw my open system or my control volume like this. Okay, so we're gonna have a velocity coming in. I'll call this V in. And then we're gonna have a velocity going out, V out. Right? And conservation of mass tells us that what comes in must go out, right? So we have that blue. We have that V in times A in is equal to V out, A out. There's a density on both sides of this equation, but the density, the fluid isn't changing from 0.1 to 0.2, so I can divide through by it, okay? Okay, and just note that these are circular areas, so we have Vn times pi d squared over 4 is equal to V out times pi lowercase d squared over 4. Everybody with me so far? Okay, cool. So we have a pi and a 1/4 that shows up on both sides of this equation, so I'm gonna divide through by those. And then I'm also going to write this as an expression for V out. So I can solve this equation for V out and say that that is just V in times uppercase d squared over lowercase d squared. All right, so we will use this in just a bit. Okay. I can also, it's the same thing to write that V out is equal to V in A in divided by A out. Right? So I can solve both of these equations in the same way. All right. Okay, so let's look at our Bernoulli equation next. So our Bernoulli equation tells us that we have pressure at the inlet plus rho V in squared divided by 2 plus rho G H in is equal to all those three terms, but for the outlet. So we have pressure at the outlet plus rho V out squared over 2 plus rho G H out. Both of our flow meter sensors are oriented horizontally, so we don't have any change in height relative to gravity from 0.1 to 0.2. So I can cancel these out because H in equals H out. All right. So far, so good? Okay. Now what I'm going to do is I am going to substitute this expression using the areas for V out, so I have everything in terms of V in. All right. It doesn't really matter. You could solve for V in and have everything in terms of V out. It doesn't matter. All right. But I'll just do it that way for now. Okay. So I have P in plus rho V in squared over 2 is equal to P out plus rho over 2. And then our V out is V in times A in divided by A out. And that whole thing is squared. Okay. Okay. So we want to find an expression for the volume flow rate. We want to find V dot, but remember V dot is a velocity times an area. So this is Vn times An. All right, so we see that it's here, right? So we just need to do a little bit of algebra. All right, so let's do that. So I'm going to move my pressures to the left-hand side. And then I'm going to rearrange my right-hand side as rho over 2 times V in squared times the quantity A in over A out squared minus 1. All right, so I've just moved rho V in squared over 2 to the right-hand side, and then factored out the rho over 2 Vn squared that shows up in both of those terms. All right. Okay, we want to get the Vn and the An together, so I'm going to factor out an An squared out of that last term here. And let me just do this in an extra step so that it is abundantly clear. So I have An squared over A out squared minus An squared divided by An squared. All right, so that's just another way of writing 1. And then I'm going to factor out the Vn squared times An squared. And I have 1 over A out squared minus 1 over An squared. Okay. And then this is equal to our volume flow rate squared, right? Okay, so this means that our P in minus P out is rho over 2 volume flow rate squared. And then I can rewrite this 1 over A out squared minus 1 over A in squared as A in squared minus A out squared divided by A out squared times A in squared. Okay. In the lab handout, this is called delta P, so I will call it delta P for now, but if you are confused about if it's in P in minus P out or P out minus P in, now you know. So we are going to solve this for volume flow rate. All right. So to do that, we have the following. So we have delta P times 2 divided by rho divided by A in squared minus A out squared divided by A in squared times A out squared. Just move this over. And then we have the square root of this whole thing. Okay, we're almost to what the equation is that's in the handout. So I'm going to rewrite this in the following way. So I have 2 delta P and then rho times, I'm going to factor out 1 over A out squared. And I have A in squared over A in squared minus A out squared divided by A in squared. All right, the 1 over A out squared, since that's in the denominator, it comes into the numerator and we're taking the square root of a square, so I can bring out the A out here. And then I have 2 delta P divided by rho 1 minus A out over A in quantity squared. And this is the expression that's in the handout. That's just kind of suddenly given to you. So now you know where it comes from. And maybe no one wanted to see that, but when I was a student, I wanted to know. So now you know. Any questions about that? Okay. So just to quickly recap, so we're basically using conservation of mass and energy to say, if I have this configuration here, I know the geometry of it, so I know the areas of my inlet and outlet. And I also am measuring the pressure at my inlet and outlet. That means that I can figure out the volume flow rate through that thing, okay? Which is essentially what we're gonna do in this lab. Okay. Also to recap, remember I went out of my way to mention how the Bernoulli equation, the energy equation that we're using, makes a bunch of assumptions. Well, that's very important for this lab, okay? We are measuring a real system. Obviously, it exists in reality, right? And this equation is a perfect idealized construct, which is going to be not the same as reality, right? So in real systems, like the one we're going to look at, the assumptions that we made to use the Bernoulli equation don't usually exactly hold. In particular, this system is not fully frictionless. Another way of thinking about this is there's losses present in this system, all right? So there's going to be inefficiencies. Inefficiencies generally come from friction and so forth. So because of this, typically what we need to do is calibrate a flow meter like one of these with a discharge coefficient. So this is given the symbol C sub D, discharge coefficient. And how we're going to do that is like this. So we will say that we have the volume flow rate that's real. So our actual volume flow rate is equal to our coefficient of discharge times the idealized volume flow rate. Okay, so this is the volume flow rate based on delta P and the Bernoulli equation. Right? And then CD is going to capture or adjust for departures from idealized systems. Does that make sense? Okay. Okay, so we want to look at our Venturi meter, our orifice plate meter, and then we also have that vertical flow meter, variable area flow meter that we have on our experimental equipment. These are all things that we're going to need to essentially calibrate, or we'll have an error associated with them. So we need some sort of a ground truth. And so what we're going to use for that is the volume collection method of measuring volume flow rate. So volume flow rate is how much fluid passed through a system per unit time. So we can calculate volume flow rate by measuring the amount of fluid that exits a system, as well as how long it took. So essentially what we have is for the volume flow rate of collection, so this is collection method, is equal to the volume that accrues over the time it took to accrue it. There's obviously more than one way to do this. You can, for example, have an empty tank, set your stopwatch to go, and then decide you're going to measure how much volume is in there in 1 minute. That's usually not the best way to approach it because you have to read the scale like as fast as you possibly can. So it's very hard to do it this way. I suggest picking an amount of volume, and then once you get to it, you stop the timer, and then that's the amount of time that you would use. So if you say, I want to time how long it takes to get to 1 liter of collection, you have somebody on your team watching the volume collection area, and once it hits 1 liter, the person with the stopwatch hits stop. Does that make sense? Okay, cool. So essentially we are going to be we're going to compute discharge coefficients for the Venturi and the orifice plate meter. And then we're going to be comparing against our volume collection method, which we're going to assume is the truth. Okay, so we're going to take that to be the perfect volume flow rate. Any questions so far? Okay, so let's have a look at the apparatus. That's like mostly in view. Okay, so this is our experimental apparatus. This is our variable area volume flow rate meter. We're not calibrating this one, but we are going to record its measurement. So you'll see that it has marks on it for liters per minute. So make note of kind of the smallest scale on here and make sure that you record it for each test that you do. Our Venturi flow meter is right here, so you can see through this plastic, the constriction in here. And then you'll notice that there are two tubes connected, one at the inlet. So water is going to come in this way, flow up and around and then out. And then we have another pressure tap at the constriction here. So all these tubes are connected to a barometer or barometers. All right. So we're going to be recording the pressure readings for the inlet and outlet of the Venturi meter, as well as the constriction one up here. So this is the one that's the more severe constriction. It's hard to see through here. But 6 is your inlet and 7 is your outlet. That should be marked also in the lab handout as well. Maybe not this sheet, but it's marked on the more verbose one. Here's our flow control valve. We're going to use this. And then the bleed valve is this shiny one right here. And then the bench valve is the blue one down here. Okay, so these are the 3 knobs that you're going to use in this experiment. Oh, and there is, sorry, it's going to be hard for some of you to see this, but you can see it on your way out. This is where you're going to measure the volume that's collected. So when it's empty, it's down here. And then you're going to want to make note of how many liters. Like I said, I would suggest, picking a volume and then having someone stop the watch when you get to that spot. Okay. Does that make sense? And then this is a stopper for the drain in here. So I can, why don't we do that? I'll turn this on and kind of show you. The blue knob is kind of stinky, so it'll seem like you've hit all the way open, but you have to push the button. Okay, so I've got water coming all the way into this tank here. And you can see that it's starting to go up. So this water level will start to go up, and that's based on what's collected in the drain here. So if you want to measure the volume being collected, you got to make sure to plug the drain first. Okay. If you unplug it, then it will measure nothing. Okay. Okay, so make sure that sorry, that's very loud. For each test, you're going to want to make sure you start with an empty, tank in here, pull the drain out. Once it resets, then you can go again. Okay. When you come to the lab, the first thing that you're going to want to do is make sure that you have all of these knobs all the way closed. This experiment, I think, is, in my opinion anyways, the most touchy in terms of getting it set up. There's a little bit of a feel for it, but I tried to make the sort of step-by-step instructions that are in these notes such that it doesn't take you too long to kind of get the idea of how to make it work. So you'll come in, verify that all the valves are shut all the way. And then what you're going to do next is you're going to open the flow control valve, so the red valve, and then the bench valve, that's the blue one. All right. And then we're going to turn it on. So essentially, we're putting water through this entire system. We want to work out all of the bubbles in here. And next, we're going to turn off the flow from the bench. So we're going to tighten the blue knob and then purge out any bubbles that we might see on the manometer. And the idea is to get your barometer to about this level, so like halfway. And the reason for that is when the pressure increases, we don't want the barometer to be overfilling, right? So when I open this, it's going up a little bit. And then, so I put a little bit of flow through here. And you can see it starting to move. And it's probably hard to appreciate, but very small adjustments to the control valves will cause this to change very quickly. So the name of the game really is to move quite slow with how you're adjusting these. And then if you ever get yourself into a position of the barometers being overflowing, just start from the beginning. Close all the valves, turn it off, start again. That's completely fine. So what we're going to do next is I'm going to increase very slowly the flow rate. And I'm going to be watching this gauge here. I've already done it. So you can see this little weight in here. Actually, just to clarify, so the top of this surface is where you're going to read the flow rate off of, not the bottom. And so typically you want to start at the higher flow rate. So you're going to be collecting values between, I think it's 5 and 20. So 20 is the top of this. Okay, this is actually pretty okay. So I probably can't see from back there, but if you want to come up and walk around, the highest value on my manometer is right here. And then the lowest one is down here. Okay. And so, once you get this set up, what you would do is you would, measure what this says, measure all your barometer readings that you need to record. And then when your stopwatch person is ready and the person to measure the volume is ready, you'll plug the tank and then measure how much volume you collect over a set amount of time. Okay. When you adjust to different flow rates, you want to go low and slow, okay? So that you don't have the barometer go out of balance. You can adjust the flow rate through the bench valve or through this control valve. This one is less sensitive. All right, so this one, you have to turn it many more times for it to translate to movement there. So I'm turning it a number of times. It still really hasn't adjusted too much. You can start to see it go down now. And as you're doing this, it's good to go nice and slow because you'll see that the barometer will kick up for a second and then it kind of settles back down. So now we're at about 19. All right, and so that's essentially what you do for the lab. So you get this set up, go to the highest flow rate first. And as you're measuring your flow rates down from here, just take it easy and everything should be fine. If you go too fast and it over bubbles and you get it all wonky and it's not reading anything, then just start over. Okay, are there questions on how to do this? Feels okay? Okay. I'm gonna turn this off so I don't have to shout. And I'm gonna close these off. So it's ready to go. Yes. So again, this is all largely recreated from the lab handout that's on Moodle. this right here is the step-by-step of how I have a couple of times repeatedly gotten that working without issues. It might vary a little bit from what's in the official lab handout, so I'd suggest use this procedure for getting the barometer all set up. And then in terms of collecting data, the analysis that you're expected to do is for every measured flow rate, you're going to calculate and tabulate the volume collection flow rate values, the idealized Venturi and orifice meter flow rates. So using the Bernoulli equation that we had talked about. And then you're also going to record the variable area flow rate meter. And make a note, this is in the lab report and it's here, but the uncertainty for that one is given to you. It's 5% of the full scale of the flow meter. So just check out what the max value it can read, and then its uncertainty is 5% of that, okay? So you're gonna have to present a table with all of that information in it. In addition, you need to make a graph of volume collection flow rate versus the ideal Venturi and orifice meter volume flow rates. So I'm gonna put this down here. So for plot 1, this is going to look like you're gonna have VDOT collection. Oop. Keep in mind that you will calculate the uncertainty for the VDOT of your collection method. So the equation is very simple. You just have a volume divided by a time, but you have uncertainty in both the measurement of volume and time. All right, so you're going to want to make note of the smallish hash mark on the flow bench for the volume collection. And then whatever kind of stopwatch you're using, if it's your iPhone or whatever phone or a stopwatch, whatever, just make sure you make note of how many digits of precision it has. And then this plot will have VDOT ideal. And you will have something that looks like this probably. So your legend will be, this is Venturi. And then you might have orifice. All right, so you're gonna have 2 data sets on the exact same plot, one for the Venturi and one for the orifice. Both of them are gonna be compared against the volume collection for the same measurement point, okay? And then on all of these, you're gonna need to show the error bars in both the vertical and horizontal direction, okay? Any questions on that so far, or does that make sense? Okay. We're not done yet. So the next thing that you're gonna wanna do is you will add a fit line for both of those sets of data. So you will have, for example, a fit line for orifice, and then a fit line for the Venturi. Okay. This lab report, we do not give you what the type of equation you should fit. So typically, the experimental data is gonna tell you kind of what the type of curve it should be, right? So if your experimental data looks exponential, do exponential. If it looks linear, do linear. And use your best judgment based on how your data looks from the lab, okay? Okay, make sure you put in the equation on the graph. And next to the equation, you will have your R squared value. Okay, so for example, something like V dot ideal equals 3 times V dot collection plus 2. I'm making this up. It will not look like that, okay? And then you might say R squared looks like 0.87. Okay? The R squared values will be printed out to the command line in MATLAB if you're using MATLAB. So you can grab that information there. Yeah,
We're making the graphs on MATLAB like we did in Lab 0.
please do, yes. I've seen a few people's Lab 0 so far and you're all doing fantastic. So
Okay, yeah.
I have complete faith in you.
Because we did like, I feel like, was it in maybe 1400 where we did like Excel tracking, like.
Yeah.
Like this, so I was.
Yep. We're gonna do MATLAB. In my class anyways. If you're not in my class, I think you're free to use Excel. Sorry, everybody in my class. Okay, so this is plot number 1. Are there questions on that? Or does it make sense? It's okay? Okay. And based on this plot, based on these fit lines, so best fit equations are to determine the discharge coefficient. Okay? A hint on what sort of a fit you should do will be related to kind of how we define the discharge coefficient. All right? Okay, cool. So now that you have your discharge coefficients, you're gonna make another table that includes the ideal Venturian orifice plate meter flow rates and the corrected one. All right, and you're gonna compare that corrected value with the variable area and the volume collection flow rates. So this table should also show a percent difference from your true data, which is the volume collection one. Okay, so that goes in a table. The second plot, you're gonna plot the flow rates determined by the 3 types of flow meters as a function of the volume flow rate from the collected method. And you're gonna use the same scales. So make sure that like if your x-axis goes from 0 to 20, your y-axis goes from 0 to 20 as well. And then on that, you want to include the line for a perfect prediction. I thought this was kind of confusing. In the lab handout, this is described as a 45-degree line, which is true. Essentially, you want to plot the line of a perfect prediction. So like, what would it look like if your model was perfect? So for example, if you have V dot collection and then V dot of some other method. So if your prediction was absolutely correct, you would have a 1-to-1 line. Right? So this is ideal. Or perfect, I guess I should say. Right? So chances are your data is not going to fall right on that perfect line because we've got friction in that system, right? So it's not going to be perfect. So you want to have that on your plot and then and then you're gonna, on this plot, you're gonna also include, you'll have your venturi. You're gonna have the orifice. And then you're also going to include the variable area one. And then obviously make sure you include the error bars on this one as well. Okay. Okay. So these are the tables and plots. In the lab handout is essentially an example of the tables in terms of formatting and what you should include in there. So make sure you have a look at that. I didn't replicate it here. And then in your conclusions, we have guided you with some questions that you should be sure to answer as you're discussing your data and your figures and your tables. And they are a discussion about which flow meter is the most accurate. All right, so which one got closest to predicting your volume collection method data? How could you improve experimental uncertainties with the volume collection? What types of applications would each of these flow meters be best suited for? What are the pros and cons of each flow meter? That kind of ties in with the previous question. And then finally, make sure that you cite any references that you might use. So answering C and D, I'd imagine you might do a little investigating and find some other references to use. So make sure you're citing those and justifying their validity. All right, so make sure they're coming from good sources. Does that make sense? And this is the gist of lab 1. Are there any questions broadly speaking? No? Yeah,
We're taking a time measurement.
yep.
Yeah, the uncertainty for that. I feel like I might end up having a stopwatch because less uncertainty than just me pressing a button.
Oh, sure. So you're asking about the human error?
Yeah.
With pressing it on time? So that's a good question. The kind of half of the smallest digit that it reads is supposed to account for that. Whether it does in reality, perhaps not, but that's the assumption we're gonna work with. Does that make sense?
Yeah.
Cool. Other questions? No? If not, I will release you. If anybody wants to try out the flow bench before you go, that's fine. Oh, actually, before you go, anyone who is registered for any of my sections on sale should have swipe access to get into this lab now or within the next like 24 hours. And now that you've been to the demo, you're free to go and sign up your team to come and collect data on the spreadsheet. Okay? Cool. All right. That's all.